My name is Carol Hood. I'm a professor of physics at Cal State San Bernardino and associate director of the CalBridge program. Given what happened earlier today, I'd like to read a short statement and then we'll start to introduce our speakers. This afternoon, a jury in Minneapolis found former police officer Derek Chauvin guilty of murdering George Floyd. While this verdict holds Derek Chauvin accountable for his actions, it does not change the systems of oppression and violence in place that allowed George Floyd to be murdered in the first place. This outcome is only one step in addressing the impacts that police violence has on our culture. We all have a shared responsibility to build a system of public safety that protects everyone equally, and we must work to end racist practices, especially in Black and Brown communities that have suffered most under the current system. We join others in demanding not only just accountability for past injustices, but action to prevent future tragedies. We hope you make time to learn more about organizations working throughout the country to make change and to support their important work. We will continue to uplift the work of generations of organizers and a central message of the protest sparked in George Floyd's honor. Black Lives Matter. All right, so to move us forward, for those who have been invited here today, we have two speakers. Becky Flores is a graduate of CSU Northridge, and a CalBridge alum. She was part of cohort 4, if I remember correctly, or wrote correctly. And she's now a PhD student at Georgia State. She'll be our first speaker. About halfway through the hour, we'll then wrap things up and switch to our second speaker, Eleanor Lyke. If you have questions throughout the talk, please utilize the Q&A button as opposed to the chat to post your questions. And we'll go through and take a look at those at the end of each section for today's talk. So with that, Becky, do you want to go ahead and share your screen and get us started?
Yeah.
Well, why don't we just mention at the beginning, so if you're interested in attending next week or in 2 weeks talk, that one's actually going to be a special time of noon. So just to make sure that you note the different times, since the speaker is from the Netherlands, to keep it at a reasonable time for her.
Great, thank you.
Which screen are you seeing?
You look good. We're seeing your regular presenting screen.
Okay. Alrighty. So, hi everyone. Thank you for having me here. I am currently in my second year at Georgia State. So today I will be talking to you about what I've been doing for the past year, where my research is involving measuring the sizes of stars with dynamical masses. So to start off with a quick background on how we get sizes and masses, there are some indirect and direct methods that we use to get sizes. Some indirect methods involve using stellar evolution models, such as MESA, which stands for Modules for Experiments in Stellar Astrophysics. And with MESA, you're able to give it different input parameters, such as mass, and then it'll give you an evolution model and also give you a size. You can also use photometry methods, where you can use the stuff in Boltzmann law and plug in luminosity and and temperature, and then you can solve for radius that way. There are also some direct methods, such as using eclipsing binary light curves. From these light curves, you are able to measure a size, but it's important to note that for eclipsing binaries, oftentimes this means that the components are tidally locked, just like how the moon is tidally locked with the Earth, where one side is constantly facing the one side of the Earth. And so if this is happening with two stars, then that just means that they could be more active, and this can be changing their sizes. There could be mass exchange, or there could be more activity with the stars. And then another method is by using lunar flotations, where there is a star behind the moon. This works really well with really bright stars, but when this happens, there's like a flickering of the light, and this changes the diffraction pattern, and then this can be used to estimate angular size for the star. And then there's also interferometry, which is what my research uses, And interferometry is basically just when you use multiple small telescopes that can act as one big telescope. And so I mentioned getting radius and angular size. And so I just want to make sure that I can clear up what the difference between the two is. So with a radius, that's a physical size for a star. It's measured in solar radii or in kilometers, and we know the size for the sun really well. And we compare other stellar sizes to the sun. So we compare it in terms of solar radii. For angular size, what that means is the apparent diameter, or like the size that it has when you look at it in the sky. So for example, if you're a little person on Earth and you're looking at the sun, which don't do with your naked eye, but let's say you're looking at the sun has some distance, we know that to be 1 AU, and then the angle that the sun has in the sky is the angular diameter. And from this, we could also get a physical diameter. And so for the sun, because it's the closest star to us and we know the distance really well, we know the angular size for the sun. So for the sun, we know that it has a size of 0.5 degrees. We could also measure this in arc minutes or in arc seconds. And for other stars, they're a lot farther away compared to the sun. They're a lot smaller. So their sizes are typically measured in milli-arc seconds. And so for different mass methods, I'm just going to mention one. There's a direct method where you can use radial velocity measurements from binaries. And so from a binary, you need to be able to map out an orbit and get the radial velocity. And from there, you can get a dynamical mass, which are pretty accurate. And this method is really easy for short period systems, systems that have a period of about 2 days or so, a couple days, because then you can easily map out their orbit and then you can get their masses that way. But this gets really difficult for longer period systems, for systems that have a period of like 300 days or more, because that just means that you need more observing time to get a full orbit, and observing time is pretty competitive. And so what I have right here on the right is just a radial velocity curve for a binary that's in a young open cluster. And so for most stars that are nearby, such as Betelgeuse and Taurus and Rigel and Aldebaran, we know their sizes and masses pretty well. These are really big and bright stars. We can see them with our naked eye. And so we know their sizes pretty well. And we also know the size of our sun. It's our closest star to us. And so on the smaller end, we also know the sizes and masses really well for like stars such as Proxima Centauri. For Proxima Centauri, for Teid-1, and for Gliese 229b. And then for Gliese 229b, that's actually a T-dwarf. So we know the sizes for most stars from different spectral types. However, although we know the sizes for these stars, we still don't know the masses and sizes for most stars in the Milky Way. And this is partly because the farther away you get, the harder it is to resolve a star. So it's almost as if you're trying to measure the size of a nickel that's almost nearly 10,000 miles away. It gets really difficult. And so this is what motivates my research. And so in a study that was done by Torres et al. 2010, out of 118 systems that he observed, 81% or 95 were all eclipsing systems. And so most stars that have both mass and radii measurements are in short period eclipsing binary systems. And so what this means is that oftentimes with these eclipsing systems, it just means that they could have components that are interacting, such as this image down here, where it's an image of a binary. They could be interacting, there could be some mass exchange, they could be tidally locked, chromospherically active, or have inflated radii. And so because of this, there's a bias towards short period systems, and it makes it really hard to account for these interactions, and it can affect their mass radius relationships. And then this also influences stellar evolution models. And so we see this a lot, especially for lower mass systems, where especially for M-dwarfs, where models consistently underpredict radius measurements up to 4%. So there's a discrepancy between observations and models. And so with my research, my goal is to hopefully see if we can overcome this bias. And instead of getting the sizes from eclipsing system, let's get the sizes of long period wide binaries that have known masses, known dynamical masses. And this would be important because we'll be able to improve, hopefully, stellar evolution models, and hopefully we can bridge that gap between the discrepancy. And having accurate sizes, a radius is a fundamental parameter. And so we can have accurate stellar sizes, then we could also get accurate exoplanet sizes. If you know the size of the host star, then you can get the size of the planet. And so exoplanets are a really big thing right now. So it's really important that we can get the sizes. And so we propose to do this by using long baseline interferometry. And so let's talk about interferometry for a bit. So interferometry, again, it's when you use multiple telescopes at once so that it acts as one big telescope. Currently, our biggest telescopes right now are about 10-meter telescopes, like 10.2 or so. But if the bigger that you get, the better resolution that you get on a target. And so the bigger, the better, but also that means it's more expensive and you start getting effects from having a heavy mirror. And so to overcome that, we can use interferometry. So for example, in Chile, there's the VLTI, where it uses 4 8.2-meter telescopes and then another 4 1.8-meter telescopes. And so with this interferometer, you get really good resolution at near to mid-infrared wavelengths. And it's really good to do research on young pre-main sequence stars and up to extragalactic objects such as AGN. There's also the Navy Precision Optical Interferometer in Flagstaff, Arizona, where it is in a Y layout and it uses 6 telescopes. It is currently still under construction, but it will eventually have a baseline distance of 430 meters. And with this interferometer, its purpose is to measure precise positions of the stars so that we can have precise positions on Earth and in space, and it's good for timekeeping. Then last but not least, we have Chara, the Center for High Angular Resolution Astronomy Array, which is located on Mount Wilson, California. And Chara is currently the best interferometer. It has really good resolution and it has a long baseline of 330 meters. This is currently the longest. And they recently got funding, so they're going to expand and add more telescopes. And so it has a Y configuration, and it has 6 1-meter telescopes that it can use. And so you can use a combination of 2 to 6 telescopes at once. And so how does Chara work? So Chara measures the light from a star using 2 or more telescopes that are separated by some distance, which is the baseline. And so the resolution is set to the baseline length, where the larger the baseline and the better the resolution that you have. And so the fact that it has a baseline of 330 meters, that means that it acts as a telescope that has a 300-meter diameter, which is pretty great. And so we have 2 telescopes, for example, and if we're looking at a star, light from the star will hit both of those telescopes. But because these telescopes are at different positions, light is going to hit those telescopes at different times, and it's going to travel at different distances. And so then once the light hits those telescopes, it travels to a beam combining lab where the light, where the time difference and the path difference is then corrected. And so it acts as if the light hit one telescope at one time at the same time. And so once this happens, we get fringes. And so fringes, what Chara does is measures the amplitude of these fringes to get a visibility measurement. So from the visibility, it measures the maximum and minimum of the fringes. And what I have right here is a waterfall plot, but what it is a stack of interference fringes. And so this is what we get when we're observing the star. And so for these fringes, when we get these fringes can give you sizes. And so for small stars, for stars that have an angular diameter of less than 0.25 milliarc seconds, the fringes will be, the fringe contrast will be high. But if we have a large star, something that's greater than 5.5 to 3 milliarc seconds, the fringes will be small. So this is because if you have a larger star, we have light coming from both ends of the star at like different times and at different paths. So then the parts of the star will interfere at different path lengths. And so then this gets translated to something that's smaller. So then once we have the visibility measurements from the fringes, we get a plot, we can make a plot of visibility versus baseline. And we can plot the visibilities to a Bessel function. And so it's a pretty complicated function, but essentially this Bessel function is dependent on angular diameter, baseline, and wavelength. And so if we fit the visibility points to the Bessel function, then we can get a size. So in this blue curve, we have a size. It gives a size for a 1 milliarc second star. And then this red curve is for a bigger star that is 3 milliarc seconds. And then from these curves, we also get these lobes, which also contain information about a star's shape or different surface features such as star spots. And so Chara has 4 beam combiners currently, such as Classic, Climb, Merc-X, and Pavo. And so these beam combiners can use up a combination of 2 to 6 telescopes. They have different magnitude limits and they have different science drives. So some of them are really good for diameters, looking at binaries, disks, or they're really good for imaging. And so for my research right now, we are using Classic because it has the faintest magnitude limit in the infrared, and it's good for diameters. And currently also they have 2 new beam combiners that are under development. And so to show off Chara a little bit, some cool stuff that Chara has been able to do is that I've shown this picture already, but it has been able to image interacting binaries. So this is an actual image of Beta Lyrae, and you can see how there's some mass exchange going on. It has also been able to get some first images of a nova during the early fireball stage. So here we have angular diameter versus time. And so we can image the nova between 3 days to 7 days. It has also been able to image star spots on a star. And it has also been able to detect warped planetary disks and also measure sizes. And so this is what my research is focusing on. But what Chara has been able to do, and what this group, Van Braun and Boisjan, has been able to do, is get the sizes for most stars spanning the HR diagram. And so what makes my research different is that for most of these stars, most of these are single stars, or if they are in binaries, then it's only a size for the primary component. So for my research, what I am focusing on is getting the sizes for both components in a binary. And so I have 6 binaries. This is an ecliptic map, and this is where they are located. So they are all above a declination of -25, and they are within a distance of they are within a distance of 25 parsecs. I have 3 M-dwarf pairs and 3 FG pairs. And for the exception of 1, they all have a period of greater than 300 days. And so with these targets, because they are in wide systems, there's no interaction going on between them like with short period eclipsing systems. And all of these have known dynamical masses. And so to talk about what my research has been focusing on in this past year, we have a target called GJ570BC. This target is part of a quadruple system where the A component is an A star, and then we have B and C, which is an M-dwarf pair, and then the D component is a brown dwarf. So it's a pretty interesting system. It has known masses for both B and C. It has a distance of 5.8 parsecs, so it's pretty close, in a period of 309 days. And so here we have an orbital plot where the primary is at the crosshairs, And then we observed the system, both components, in May of 2013, where one of the components was here, and then in June, where the second component was pretty close to the primary. We also have scheduled time to reobserve this system this weekend in April. So we're going to reobserve it this weekend and later this year in June. And so for this system, it's really interesting. However, because it's very eccentric, it kind of gives some issues. So first, the way that we're getting the sizes for this system is through a method called separate fringe packet analysis. And so with this analysis method, typically it's been used to measure the sizes of single stars, but it's also been used to detect binaries and to map their orbits, but it hasn't been used to obtain the sizes of both components in a binary. And this is primarily because if you have two stars in the sky, when you're observing them, you can get extra contaminating flux. You can get extra light from the partner onto the star. And so you have to be able to correct for that. And so this has been limited in the past because there was, you need to have accurate flux ratios to be able to correct for that extra flux. But our targets have accurate flux ratios, so we can get their visibilities. Here's that same equation from before, and we can apply a correction where we can add their flux ratio and correct for that. So here I have an image of a scan where we have a fringe packet for GJ570b, and we have a fringe packet for GJ570c. And so we are able to get sizes for both components separately after applying the correction. However, because in June it was very close, this ends up giving us overlapping fringe packets. And so when this happens, we have a scan for GJ570. We get two fringes, which is for both components in one scan. And so currently with this analysis method, it treats both fringes from both components as one, and it only gives you one size instead of two sizes for both components. And so our method can't differentiate the two. And so there's no way to analyze the data that we have from June. And so currently, that is what I am working on right now. So hopefully we will be able to get separate sizes from overlapping fringes. And this will be very beneficial in the future so that we could observe targets, eccentric targets like GJ570 during any time of the year. We're not just limited to when they only have separate fringes. And then the second target that I've been working on is HD 239960. It's an M2 and an M4 binary. It's possible that it has a ton. It hasn't really been confirmed, and there's been papers saying that there's a comet that originates from this system, but it's not confirmed. But here is the orbit for this system, and we observed it last year in September. So this is where the secondary component was, and we propose to observe it again later this year. And so because this system has a period of 47 years, we currently only have a system mass for now. However, research from another scientist, Andrew Mann, he's working on getting component masses. And so this binary is also really close at 4 parsecs. It has a really wide separation. And so this would be really good to use as separate fringe packet, use for our separate fringe packet analysis. And so when we observed it in September, the secondary is pretty faint, so we weren't able to observe it that time. We only had one night, so we mainly focused on observing the primary. And so after looking at these two binaries, what are preliminary results? These are my preliminary results. So for GJ570b, we know that it has a predicted size of 0.834 milliarcseconds. I was able to get a predicted size from using its flux ratios. However, when we get our visibility plot, we have visibility and baseline, and here is the Bessel function, we get a best fit diameter through our data points of 0.92. So it's a bit bigger than what we expect, but it's not too bad. However, for GJ570c, we have a predicted size of 0.58, and it's a fainter companion, so it should be smaller. However, we get a size of 1.2 milliarc seconds, and the fit isn't going through all of the data points, and we don't know why. So this data was observed in 2013. I think I was still in high school. And so as of right now, we are trying to figure out what's going on with the data, trying to interpret it because we don't have notes. So we don't know which component is which for the data that we have. And so we're just trying to figure out right now what's going on. Maybe the way that we did the flux correction isn't working out as we expected, but we have more time coming up this weekend to observe it. And for the primary of HD 239960, we have a predicted size of 0.68, but we get a size of 0.58, and we only had one night. And for some reason, the fit isn't going through most of the data points, but we hope that with another night, hopefully we can constrain the size and then also observe the secondary. So after this is what we have so far, but we also have proposed to observe another M dwarf. It's a triple system with known masses, and it's pretty close with a really large period. And this will be observed this weekend. And then, because not that many systems have masses for wide systems, we want to expand our target list. So currently we've observed M dwarfs. So now we want to expand brighter stars. So here we have proposed to observe 3 FG binaries. And this is what their orbits look like. So they're pretty wide, and they have large periods with the exception of this one, iota peg. But we'll be able to get their sizes with Merc X. So this is a different beam combiner. So I'm really excited to learn how to use Merc X. And it's also an imaging telescope. So we'll be using a different analysis method for that one. And so in summary, with my research, we're doing pretty new science. We're getting the sizes for stars in wide binaries with Chara, which hasn't been done before, especially with the current analysis method. It hasn't been done for the targets that we have. And so as of right now, we have some preliminary sizes for both components of GJ570EC and for the primary of HD 239960. And we'll be getting more data on that. And we'll soon be able to analyze overlapping fringe packets, the June data that we had for GJ570, and get separate component sizes for that. And then we're in the midst of creating a list of stars from wide binaries with accurate masses and soon sizes ranging from F through M. And with this, we'll be able to check if the observations match stellar evolution models. So we'll be able to test that. And then again, this is really important, especially so that we can get the sizes of exoplanets if we have the sizes for stars that are accurate. And so with that, I conclude my talk.
Great, thank you, Becky. Just a reminder, and I put it in the chat as well, if anyone has any questions, please submit them using the Q&A feature. We have a few already. Would you like me to read them, Becky, or how would you prefer to proceed?
Yeah, I can see them. So what can you do with the information of the size and mass of stars? It's just for the sake of knowing, or is knowing the densities and such of stars helpful to another branch of astrophysics? Yeah, so sizes, like one of the things that it's important to have sizes for is so that we can know exoplanet sizes. I know that there's a relation where if you know the host star size, then you can get the planet size. And so if the host size is accurate, for the star, if the size is accurate for the star, then that means that you can get a pretty accurate size for the planet. Besides that, I also know that if you have the size, then like you mentioned, then you can also get density, I believe, through, what was it, astroseismology. There's a relation where you can also use the size and the mass to get density. And also with sizes, it's a fundamental thing where we have all these stars in the Milky Way and we don't know the sizes for almost all of them. So the fact that we only know them for this close ones, we want to be able to know the sizes for stars that are farther away. However, with the instruments that we have, we're a bit limited, but we're getting better. We're getting better instruments, with interferometry. So we'll soon be able to get the sizes for stars that are farther away. There's another question. How do you analyze the fringe packets? As in, what do all the lines mean? So with the fringes, so I didn't show the details of what actually happens, but you get a, so you have a fringe packet, and then so there's a program. There's a program that does the reduction for me and gives me, and calibrates it and gives me a size. But what it does, it like does some fits. It does like a Gaussian fit, and then does some like Fourier analysis, and then it can give me a visibility. So what I'm getting from these fringes is a visibility. And from the visibility, then I can get a visibility plot of the visibilities against the baseline, and then can fit a Bessel function to it, because the Bessel function depends on visibility, baseline, and wavelengths, and it can give me the diameter. So that's what the fringes are helping me get.
So sorry to interrupt, Becky. I think at this point we should transition to our second speaker, and we can come back and try and catch up on the rest of the questions after Eleanor's had a chance to speak. Okay. So thank you again so much.
Thank you.
Eleanor Lyke is our next speaker, who should be popping up momentarily. She was, or is, a graduate of CSU Long Beach, and is now at the University of Wyoming as a PhD student. And she was in our second cohort of scholars. So welcome, Eleanor, and take it away.
Thank you. Now, how about that? Can you hear me now?
Yes, sounds great.
Okay. As she said, my name is Eleanor Lyke, and I'm at the University of Wyoming and was a Calvert Scholar. And my advisor is Adam Myers at the University of Wyoming. And I'll be talking about improving quasar classifications and redshifts for large spectroscopic surveys. So this is a little bit different than what we just talked about, but we're going to go through some background information and some definitions up front so that everybody is on the same page. And I'd like to talk about the two projects that I'll be working on for my thesis, and these are sort of the two broad categories. The first is improving the spectroscopic classifications. So this is figuring out what type of object something is just from the data itself. And then the other part is finding a redshift of spectra, which is, for us right now, think of it as a proxy for distance away from us. And then we can talk about where does this all fit in the larger picture with our summary. So first, we need a brief background. This is going to get a little deep, so hopefully we can hold the questions until the end with the Q&A, but you're going to need to know some things ahead of time. First of all, I work on large-scale surveys. So the two big ones I've worked on are DESI, the Dark Energy Spectroscopic Instrument, which is a large survey, which is actually going to go on Sky next month at some point, we're hoping, and start our 5-year survey mission. And it's in New Mexico at the Tucson at the Kitt Peak Observatory. The other one I recently worked on was the Sloan Digital Sky Survey, which is, until DESI starts, is still the largest catalog of quasars and galaxies and extragalactic objects that has ever been observed. And we need to talk about how a large-scale survey actually proceeds, basically, from beginning to end. And the first part is that we take these photometric images of the sky. So this is just a picture of the night sky to a certain depth, which is like a brightness. And then we need to pick targets out of this. So we find all the different targets, and in here, the purple, for example, are, this, by the way, is not directly from this, but you get the idea. The purple, for example, is one type of object. The green is a different type of object. Sloan's mission was to look at clustering. So we want to see how these things are spread out in actual 3-dimensional or 4-dimensional spacetime. So for Sloan, and similarly in DESI will be similar, some kind of masking plate or a tile is set up with essentially the night sky with fiber optic cables that then observe the night sky through the telescope. It's processed by a supercomputer. This is the picture of the Center for High Performance Computing at the University of Utah, where this SDSS was all reduced, all the data was processed. And then once you get all this processed, you get these nice one-dimensional spectra, which you can actually start to analyze. And note that because you have, in Sloan's case, 1,000 fibers, and in DESI's case, 5,000 fibers feeding onto only a handful of digital cameras, you have these stacked spectras, and base types of spectra are all different types of objects. So the top two, for example, are galaxies. The third one's a special type of galaxy, an emission line galaxy. D and E are quasars, and F is a star. And you can see from these that just from the basics, they have some very different features. Stars have dips from this continuum down. Quasars tend to have emission, so they have positive emission, and it's very broad. Galaxies can have, these emission line galaxies also have emission, but they're very narrow. And then other types of galaxies are a mess. I'm sorry for whoever has to actually study those. So let's talk about what photometry is. This is a word that I'm going to be using a lot. Photometry, if you're unaware, is just photographic data. It's photo, it's where it comes from. So we take a picture of the night sky, and this image includes everything: stars, galaxies, quasars, nebula, planetary nebula, gas clouds, aliens, whatever's in there. And we need to figure out what these objects are, and just looking at the photometry isn't going to give us enough information. You can see some extended objects like this here. It's a galaxy. It looks sort of like a disk. That's not an accident. Galaxies tend to be extended objects. But stars and quasars are both what are called point sources. So they're essentially just a pixel or 4 pixels wide. And just looking at that, you can't necessarily tell what that is. So, for example, this red circle here is some object in the sky. We put a fiber on it at one point, and we get a spectra. And this spectra is actually for that data point on that image. And so Sloan, SDSS, the Sloan Digital Sky Survey, took this data, and it turned out to be a quasar. Thankfully, it was targeted as a quasar. We assumed it was. We can make an assumption ahead of time. But just because you can get some amount of information, you can't confirm what type of object it is until you get the spectrum. And in this case, we see this continuum here at this general level of light output from this quasar. And then you have these broad emission features that come up. That is the sort of fingerprint of a quasar. And these broad emission lines always show up in the same relative locations depending on the distance of the quasar from us. But you'll notice that this is about 7,000 angstroms across. This is about 4,500 data points for one spectrum. Generally, spectroscopy is considered one object at a time. Each fiber looks at one object unless you have accidental contamination from a nearby object. But you'll notice that photometry, you get a lot of data with one, say, 15-minute exposure. And for a spectrum, all you get is that for 15-minute exposure. So you can't just go and do spectroscopy on every object and every point in the sky. There's uncountable, essentially billions and billions. So we need to use photometry first to make our target lists, and then we come back with our spectra and say, okay, how often were we right on our targeting? So I just mentioned quasars before. So what are quasars, so that we can get that out of the way? I like to call them the angriest engines in space, because they're more of an engine or a process than they are an actual object. We know that all these large galaxies in the sky have these supermassive black holes at the centers, And in many cases, these galaxies are attracting dust and gas in huge quantities, like astronomical quantities. And this process of accretion, the dust and gas falls towards the black hole, but has to slow down. And in order to slow down, it has to shed that energy. And in shedding that energy, this black hole emits light. And that's what we see sort of in this artist's impression cartoon, where you have this gas and dust orbiting around a black hole center, which is obscured since it's this disk, and in this case could be obscured because of this disk. And then light will stream out of it as that material slows down. So it's a black hole that shines light, which is, I know, an odd thing. But because these are supermassive black holes at the centers of galaxies, they shed so much light, they outshine their entire galaxy combined, which is why it appears as a point source and not as an extended object. It is, but something that is that bright can then be seen very far away as well, which is very useful in our research. I want to talk about Redshift real quick because it's going to come up. So Redshift is something you've probably seen in other contexts. What we're using there is cosmological redshift. It's very similar to a Doppler shift for a police siren or something you've heard going by. The wavelength is long or the wavelength gets shorter as it's coming towards you, and it lengthens as it leaves away from you. Light's no different. Blue is a shorter wavelength. Red is a longer wavelength. Radio astronomer probably put this image together because it's reversed. However, for cosmological redshift, since the Hubble's law, everything far away from us is also moving away from us due to the expansion of the universe and space-time, all of our spectra get redshifted. So, for example, this line here, if this is a rest, so say this was, as an example, was in our solar system, something that would be moving away from us, this line now moves more towards the red, and if it's moving towards us, that same line will move more towards the blue. And you'll notice that the pattern of lines hasn't changed. They've just sort of stretched and changed their position, but the actual relative pattern hasn't changed. And for us, because of the Hubble's law and other cosmological principles, your redshift is actually a proxy for distance. If you know how much it's redshifted, you can figure out how much the universe has expanded between the time that light was emitted and when it got to us. And then you can figure out what a distance is based on a model of the universe. Okay, so that should get us set up for what I'll be talking about for this project. The first part is improving spectroscopic classifications, probably. So I just mentioned DESI. It's the Dark Energy Spectroscopic Instrument. It's actually a large-scale survey. It has 5,000 fiber optic observation nodes. Each one is on its own robotic positioner. And so for a given tile, which is these 5,000, they will have all 5,000 point to their respective objects, and then they'll take an observation for roughly 15 minutes. And then we get 5,000 spectra at a time, which is until now, the largest was Sloan, which was 1,000 spectra at a time. This means that DESI is expecting over the next 5 years to get 30 million spectra of extragalactic targets in the next 5 years, and Sloan was able to do about 4.5 million spectra over the course of about 15 years. So this is what's going to motivate this project on why we have to improve these classifications. PDF, this is not referring to the Adobe file format. This is a probability distribution function. So this is just that bell curve you see, or if the probability is a different function, we'll be using those. And then just to mention that machine learning gets thrown around a lot, especially in terms of, say, big data and astronomy, especially recently, is a computer algorithm that can change parameters and find a fit, like Becky talked about to some degree. automatically, though. It finds this fit, but it creates a mathematical model from current representative data to predict the results of future data. It has nothing to do with your current data. It has everything to do with your future data, assuming that your current data looks like your future data as far as sources of error, colors, all these other limitations. As long as the current data looks like future data, you're hoping to make predictions on that. Unfortunately, that mathematical part's in red for a reason. This is purely mathematical. It has nothing to do with physics unless the user actually inputs physical parameters as part of their defined ranges that it can choose between, which means it can come up with mathematical solutions that have no basis in reality. And you won't necessarily know that if you didn't set that up ahead of time. So it has limitations in how it can be applied to certain physical principles. So this is sort of what the project breaks down to as an image. We have, out of this 30 million extragalactic sources, a certain number of targets that we believe are quasars. And that's this blue box here. This is the quasar targets. These are the things we think are quasars, but no, not 100% yet because we don't have spectra. You take all the spectra, and then you have to figure out, or I have to figure out, which one are actually quasars, this blue dash box. Which ones, this automated pipeline that we already have that classifies everything. It classifies and finds a redshift for everything, but it's not perfect. What did it identify as a quasar? And then from my work with Sloan and now moving forward with DESI, we build this quasar, a catalog of these quasars by adding extra methods for finding quasars. So, for example, these quasars here were targeted as quasars, but the pipeline didn't hit them. It classified it as a galaxy, or it classified it as a star. But I was able to recover it by one or two methods. Whereas these targets here are objects that we target as a quasar. All of my algorithms said are a quasar. The pipeline said was a quasar, not actually a quasar. And until somebody goes and looks at it, you might not know that. And because we're taking 30 million spectra over 5 years, and a single person can reasonably look at 500 a week, you would need teams of hundreds of people in order to actually look at all of these spectra in a timely manner. I did the calculations once for just me, and it was, longer than my lifetime by at least a factor of 2 to get through some of these data sets. So we need automated methods, and our automated methods currently do not have the accuracy or the precision that we need. And this light gray area here, things that were targeted as a quasar but aren't actually, these are typically called contaminants or contamination. And then our other metric is, in my quasar catalog, how many of these true quasars did I actually find? That's a completeness metric. So from Sloan, for the last catalog, we had a contamination of 0.3%. So that means, 0.3% of the objects in the catalog aren't actually quasars, or you could say any randomly chosen quasar or any randomly chosen object in the catalog, there's a 0.3% chance it's not a quasar. Our completeness is important for clustering measurements, where you need to have observed as many of the quasars or galaxies in a region of the sky as possible. And we hit 99.8% completeness for the objects that we can see. So this isn't so the DESI spectroscopic pipeline, and a pipeline is just a series of programs or scripts, typically in Python, sometimes C++ or C#, that processes the data, makes some decisions, and then writes out all of that data that it picked up to somewhere else. So the spectrum isn't changed, it just has to fit, say, a template. And in this case, I don't know how well it shows up. Say this model, this green line here, is what the pipeline thought this object, the best template spectrum that matched this object's actual spectrum, which is in black. And you'll notice it did not actually match this magnesium 2 line. It did not match the H beta complex over here. It okay matched the O3, this O3 oxygen 3 line here. And because of that, it picked this object, and this is the best fit. This is what I was talking about mathematically. We have a broad emission line. This is immediately a quasar. We already know this is a quasar by looking at it. But the pipeline doesn't know that because it's trying to match the whole spectrum. And its top 2 fits were a galaxy at different redshifts. Which means if you took the best model fit and the second best model fit, it thought it was a galaxy. You had to hit the third best model fit before it figured out that it might be a quasar. And its redshift was very wrong. 1.86 and the actual redshift is 0.5. So this is a failure mode from Sloan, and the DESI spectroscopic pipeline is very similar. Currently can't share any data from DESI since it's under embargo right now. We haven't gone on Sky yet, but this is pretty much the same thing from Sloan, except we'll have better resolution from DESI. And so in this case, even though the spectrum is clearly a quasar from, say, my perspective as an expert, the computer wasn't able to actually make this decision. So how, without having to go back and look at all of them, how do we fix this? Well, the spectroscopic pipeline is well named because it only includes the spectra or the spectrum as data. It only looks at the spectrum. It fits a bunch of templates to it. It figures which template's the best, and then that's what it calls the object. But we took photometric data in order to target the object in the first place. WISE, the Wide Field Infrared Sky Exploration, took data in infrared, near infrared, for millions of objects. Sloan took data in optical for millions of objects. GALEX, an old survey from the 90s, took, or maybe it's the early 2000s, took information in the UV. None of this data, though, is used when actually trying to figure out what the object is. But we already have this data, so why not use it for the classifications? So that's what I'll be working on, is to pair this spectroscopic data that we have with existing photometric data that is actually fairly modular, so it can incorporate data that we don't even know exists yet, and then make a better prediction based on that. And because we're doing this without a machine learning algorithm, we can incorporate all of the physics we want without having to worry about merely mathematical solutions. So for example, this is an example of photometric data in use. If you do this, what's called a color cut, so you have the color in Sloan and you subtract the color in WISE, and then you plot that against two other Sloan colors, the G band and the I band, and you put all of the objects in this map, you can draw a line and quasars appear generally above this line. And since this is just a two-dimensional space, it's a fairly easy way to make a PDF, a probability distribution function, to figure out, okay, if it's on this side of the line, that's a quasar. But if it couldn't decide between star and quasar from the spectrum, now it can figure out that it's a quasar. Okay. And then real quickly to talk about redshifting, just to get this, we saw broad emission lines in the quasar spectrum. However, a broad emission line is what it says, broad. It's got this width of roughly 10 pixels. A narrow emission line usually has a width of anywhere between 1 to 2 pixels wide. And then you have something called features, which are these, which could be other objects which aren't an emission or an absorption sort of situation. And they're just a change in the spectrum due to a physical process or a limit. You'll notice that when we talked about redshifting, you should look at the centroid, the center of these emission lines, to figure out how far they've shifted. So this should normally appear at 1549, but now it's appearing at 7100. It's a real simple equation to figure out what that redshift value is, a z value. But you need to know where the center of the line is. And if you look at this carbon-4 line, that's not easy to find. If you look at this Lyman alpha line, which should be above the continuum, it's been suppressed because of some absorption. Where do you find the centroid in this one? Narrow lines being only 1 to 2 pixels wide, the centroid is not in question anymore. So if you can find a known narrow line, then you can find much better redshifts. Or, for example, this feature, the Lyman limit in this case. The Lyman limit is based on a physical process. That is 911 angstroms, which corresponds to 13.6 eV, which is a famous number, which is the ionization for hydrogen. So once that electron's gone, you're not going to have anything else. And that redshifts as well. It's still light, but because it's a hard physical limit, you don't have to worry about centroids. You don't have to worry about if it's asymmetric or anything like that. You can just say, all right, where's that limit? There it is. Which you'll notice on Sloan and DESI, all of my spectra have been between 3,600 and 10,400 angstroms. This is visible wavelengths only, and 912 angstroms is in UV or X. I think that's X-ray. Starting to get an X-ray. So it needs to be far away before it disappears. That's what we're looking for. Is I'll be writing an automated finder that actually looks for narrow lines and these features and sees if it can correct this redshift based on the templates. And once you know it's a quasar, you don't need to throw a program at it that has to figure out both redshift and classification, just one or the other. And that makes it specialized, which makes it much easier or much more accurate in the long run. All right. So let's talk about our takeaways here. We're looking at the large scale spectroscopic surveys are looking at studying the universe and the physical principles. So we're looking for things like the Hubble constant, the amount of matter. DESI is named dark energy because it's looking for the dark energy parameters. But in order to do that, we need a vast number of observations. And the number of observations we need to get more accurate is only getting bigger. And we have long since passed with those large surveys the size of a data set that a human beings can look at reasonably. Wouldn't you rather have something that goes and finds all of the good spectra or all of the interesting ones to look at, rather than looking at a whole bunch of ones that look the same over and over again, but are great for our clustering data? So we need something that can do this in an automated fashion. This is the same big data problem that exists in pretty much every industry that's coming. And so we'll be working on automated computers that use data that exists, but is currently unused for these applications to improve all of this. And it's all public data. So this is the kind of thing that other people can, get interested in, or that we can use for a number of applications. Thanks. Any questions?
All right. Thank you so much, Eleanor. So as I mentioned before, please submit any questions you have using that Q&A feature. We do have a few in here already. I'm going to skip some of the ones. I think the ones for your talk started, it's timestamped around 4:53, but I'm happy to read them out if that's easier for you.
I know I have them here. No, so the automated methods, so the question was, the automated methods are just theoretical and need further human input to narrow down true quasars? No, those are actually a number of templates that are created for sort of archetype galaxies, quasars, and stars. We got stars pretty well down as far as template spectra. And it just compares all of the template spectra and then which are created from real data somewhere else and figures out which one is the best template spectra. Unfortunately, it doesn't know how to say it's a quasar plus a galaxy or anything like that, but these are based on data. They're not just theoretical. Hope that answered that question. The next one's the spectroscopic pipeline also lets you know about the presence of elements. Yes. Well, I mean, what do you mean by elements, I guess is the question there. If you mean by elements on the periodic table, yes. If you mean elements of like just things in the just features in the spectrum, not really. It just gives us a redshift and a class. It tells us what type of object it is and how far away it is. The next, so it's like using pre-existing equations to analyze a situation. I think so. I'm not sure what you're getting at with that one. Was there a specific slide that you were referencing in that one that I can look at? Maybe that one's better afterwards. Is this where machine learning comes in? No, the whole point is that machine learning doesn't come into any part of this process. Because it's a purely mathematical and unphysical solution, we do not want to use it for DESI because a mathematical solution cannot tell you about physics. But the physical, if you input the physics beforehand, you can check and see if your physics is correct. But if it just pops out, say machine learning's black box just pops out information with unphysical answers, that doesn't tell you anything about the actual physics of the situation. So we're trying to avoid machine learning, but using some of the mathematical principles behind them, but making it specific and physical first. That answer all the questions?
All right, does anyone else have any questions for either of our speakers? We can open it up to questions for Becky or for Eleanor at this point.
Should I stop sharing?
Sure, that sounds great, thank you. So if we don't have anything else coming through, and I'll try and talk for a moment in case people are furiously typing for this event. For our undergrad students, we often, if the speakers have time, to stay after and have a more informal chat. So we are after 5 now at this point. So unless another important question pops up, I think that maybe we'll go ahead and end things. And then again, undergrads, if you want to hang around, we can bring you in to the main conversation here and have you or give you an opportunity to chat with either of our speakers today. So again, I just want to thank both of you so much for coming. I love hearing about the work that you're both doing right now. And it's nice to see your shiny, happy faces.